our speaker is Alexei Oblomkov.
Thanks a lot for the invitation. It's a great honor to be here, and yeah, so I'm really thankful to Andrei and Pasha for teaching me mathematics, and the things which I will talk today is basically perfect fusions of things which I learned from both of them. So basically this project about HOMFLY polynomial grew first looking at this DT-PT spaces and using like large n-duality to connect with HOMFLY polynomial. Then we looked at the torus knots, and I discovered that I see the double affine Heike algebras there. So I was really lucky to have such teachers. So, and eventually it grew into some kind of more and more topological, more physical things somehow. Basically story of this of the talk, so that at some point I went to Montreal and give a talk, and I met Lev Rozansky, and he started talking with me about this physical approach to the conjectures which I explained, and again that's something that I learned from Pasha and Andrei, so that when physicists talk to you, you should pay attention. Even if you don't understand anything, you should keep talking, and eventually things will work. So, and that will happen. So, and I will report on that. So I'll leave out like most of the physics. So I gave other talks about it, and I will talk about some.
Yeah, you should keep talking to physics rather than keep listening, because you won't understand
Exactly.
anything anyway.
Exactly. You have to interrupt and kind of ask questions. Otherwise, it's just, yeah. And you have to iterate many, many times. So, and even if I understand, like, 1% of what they say, that's already great. I think that's okay. So that's my 1%. So I will explain. So it's the end of the day. So I'll try to be brief and not complicated. So first of all, it's whatever I will say is it's all enjoined papers with Lev Rozansky. So it's like 7 of them now or something. So, but I will start with some simple equations. So that's, the first, I'll just remind everybody, since it's the end of the day, so I can be kind of elementary. So we all know HOMFLY polynomial, which is defined using skein relations. So that's the definition of HOMFLY polynomial. So in the picture here, this is a positive crossing, this one is negative. So and this one is resolved like this, right? So and we have to normalize it. So we normalize that value on a knot is 1. Okay. So and this way we'll define HOMFLYPT polynomial. Okay. So then it's an easy exercise for students. So that's an exercise that if I have a knot, so that means link with one component. It's a function. It's actually a polynomial of A and Q, but actually it's a palindromic polynomial. So basically, it has a property that this is true. And this equation is omnipresent. It's like this functional equation. It's actually related to functional equation for zeta functions of singular curves when k is link of a curve singularity. And it's also the same relation, the same equation as appears in a PT story, because DT story is a kind of large n duality, and basically also related to knots. And then there is this Q inverse symmetry in PT story. That's the same equation. So so that's an exercise. So then and by the way, ask any question and ask questions. So that's supposed to be kind of somewhat elementary. So then in 2000 people started generalizing the HOMFLY polynomials. They discovered this HOMFLY, the homologies. The Khavanov discovered kind of homologies which categorify SL2 invariants. Then Khavanov and Rozansky discovered this homologies which generalize, which kind of categorify HOMFLYPT polynomial. So, and basically I'll say a couple of things, but I was lucky that Eugene Gorski gave a talk about closely related questions, and he basically gave you definition of the space. So the space, it's a triply graded space, and that appeared in talk of Eugene as this trace, categorical trace in the category of Soergel bimodules. So there's a categorical trace in SBM. Okay, so, and well, let's just compute this. Since it's triply graded space, I just compute this graded dimension. So we get what people call super polynomial. And well, that was defined. I will not give details, maybe later I will say something, but this thing was defined by Khovanov and Rozansky. So Khovanov, Rozansky. Okay. So then there was a conjecture. Well, conjecture was before this theory was defined, or at least before it was published in a journal. So conjecture due to Dunfield, Gukov, and Rasmussen well, that the same kind of equation holds in this setting. So basically now we have one more variable. So by the way, what are the properties here? Well, I should write that this super polynomial, curly p, specializes to the old polynomial if we set t to equal -1. That's not a conjecture, that's a theorem. That's t equal -1. It's just your old. What? What's that? Oh, well, yeah, it would have been short. That's right. So Andre always has appreciation for like beautiful short formulas. So that should be much better than. Okay, that's. All right. So the conjecture was this. So you take this super polynomial, well, and you do the same thing with little twists. So basically, you put here this conjecture. And you know, I think this year we proved this thing. So this is me and Lev. Okay, the conjecture holds. And you know, basically that was like one of the final outcome of the long story. So basically, Eugene mentioned it. So there was some kind of way to construct a category, which is later the Hilbert scheme, and I will try to outline it. So, yeah. That's right. Yes. It's even better than that. So at the end of the day, you will see I would construct a Schiff and Hilb C2. C2 has coordinate x and y. So you flip them around, and Schiff is just symmetric with respect to flipping x and y. That's what it is. It's even better than that. Okay? Yeah, more questions? There is no shortage of bad notation in subjects, so you know there's so many like contradictions. So that, yeah, yes.
So there, I mean, do we know yet that your invariant is the same as modern?
Yes, that's the whole point. Yeah. So we know we have a theorem that our invariants are actually the same as the ones coming from Soergel bimodule. Okay. So that's not posted in archive, but that's the fact. Okay. That's new, yes, that's right. So, all right, so let's start the outlining thing. So, and I like what Rick Kenyon said about the talk should contain one idea. So I can summarize my idea while erasing it. And my idea is that matrix factorizations are cool. So, you know, whenever we have a problem, whenever we encounter some singular variety which has some kind of representation theoretical meaning, most likely there is some kind of matrix factorization lurking around, and that's what you should study. And that was the case for us. So, and actually, I think in Melissa's talk, that kind of appeared secret. The metrics of relations. So anyway, right. So what is a precise theorem? So the first theorem we proved, actually, for any link, we constructed an object in a derived category. So basically, so now I'll refine this statement. So D T Q T A. So that means we have action of three-dimensional torus, and there is some ring attached to the thing. So and the ring R is just RL. All right, and we set the grading so that degree x is equal q squared, and well, so far there was no theorem, they're just notations. So, and I didn't give you construction. There is a construction of object like this, such that it has the properties. So the first property that this object in derived category, so it's derived category of complexes, actually two periodic complexes over this ring, and the property is that this complex itself, this object in derived category, is anisotropy invariant. Isotropy invariant. The second property, that's what Matt was saying is new, that if you take this complex and you basically kill one of the x variable, you kill, for example, x variables, you said it, derived, just kill all of the x's and you left only, like you kill all y's, for example, and leave as x, then it's the same as the old Havana-Frozansky homologies, which are defined using Soergel bimodules.
So what is TQTA? Is it a torus?
Yeah, so it's a torus. It acts, basically that's so it's a C star cube. So and first two T stars act by stretching x and y, and the third A variable you kind of cannot see it. It just acts somehow on. It doesn't act on the space, but it would act on the complex. So yeah, it acts trivially. The last one acts trivially on the space, but it would act on the complex, and that's why you get triply graded vector space then.
And RL of xy is just spec of this RL?
Yeah, that's right. Yeah, I forgot to write spec. Sorry, that's a spec.
And also xy is really.
They're just polynomial.
X is what is x? X is x1 through xl.
Yeah, x is x. Whenever I write just x without indices and y without indices, just all of them.
Why write RL of xy when you already have RL equals to C of x1 xl y1?
Right. Okay. Let me just do this. So then, that means that's a lot of variables. Better? Yeah. Many A's.
Should RL
I don't quite know.
in the top
Yeah.
line be just R?
R L. Oh yeah. Sorry. Yeah. So yeah. Of course, Pasha is always right. Yes. All right. So yeah, I didn't. What do you mean? Like many framings? The A variables come from fair framing variable. Yes, that's true. It will not be topologically invariant. Yes. So you can. So basically, there is this. If you want to just talk about conjugacy invariant of the braid, yeah, you can do that. But there is always this Markov move when you have this extra strand, which you can remove by, this thing. So whenever you have something like this, and you want to remove this thing, that thing would not be satisfied.
And also in the bottom line, the tensor product, you don't need the L cells, just R of xy, right?
Well, it's a complex.
No. The bottom.
Oh, yeah, that's right. Yes, thank you. Yes, great. And Rx arrow is just when you kill all of the ones. All right, thank you. Okay, so then the third property is that these objects actually are invariant. There is some kind of involution which act on the space. So, and basically it switches x and y. It's a Fourier transform. So, and please interrupt me because I suspect that what I will tell would known to like people on A side, because what we do is some kind of B side of some story which is known to some people. And
So can you just clarify for how much?
Yes.
Even
Yeah, it's the same. So isotope invariant, that means, you draw a knot, and you can draw a knot in many different ways.
And what is not topologically?
What is not topological invariant? If I kind of kill this, A degree thing, then it would just become invariant of the closure of the braid inside of the thick torus. Basically, it means that it's an invariant of the conjugacy class of the braid.
And so if you do not remove, then
If you do not remove, then it's an invariant of the knot of. So you take a braid. Okay, let me just go slow. So you take a braid, and you close it up. So now you can do two things with this picture. You can embed it in S3 and treat it as a knot. So, or you can embed it inside of the torus, inside of thick torus. So if I don't have A variables, that would be only topological invariant of the picture inside of the thick torus. But if I embed it in sphere, it would be invariant of the of something embedded in 3 sphere. So the reason for that, if I draw a braid, so thanks, please ask questions. That's.
Can you say it in terms of the affine braid group or non-affine?
Yeah, there would be a affine braid group too. So yeah, so yeah, it would appear later. Yeah. So basically, you can also talk about conjugacy classes of affine braid group, and yeah, it does appear. You're absolutely right. Okay. More questions, please.
What is the number L, number of variables?
L. Oh, yes, thank you. So L is a number of the, it's a number of components. Particularly if it's a knot, then it's just one variable. And actually, it's a dummy variable. You can remove. Everything will be free of this variable. All right. And and maybe like one more property, which is kind of cheap. That's what I was telling, and it's kind of also comment on Vita's question. So if your link is a knot, that means L is equal 1. Then actually this E of k is free over. So basically, it's free over the x. It's free over this rk, and then basically this conjecture follows. Hence, this conjecture follows. So that means a priori you would have this derived product, and there would be some issues with that. But in this case, in case of one component, you don't have to worry about it. Okay. So, all right, that's the general statement. So, but how we got there? So, Eugene said that we were brave and defined some category. I would say we're not brave. We were scared and defined this category because what I'll define this matrix factorization is some kind of a mathematical, or rather kind of most elementary version of what's defined in papers of Kapustin, Saulin, and Rozansky. They define general so-called gauge three-dimensional topological sigma model. So for more general things, and basically what I will explain is some kind of gauge categorical sigma model, topological quantum fields, whatever. So, but the target in our case will be just group. So that's why kind of Lie algebra. That's why things are simple. But I will not talk about that. I'll just talk about matrix factorization. All right. So what is the magic object? The magic object, which I will explain slowly. So I'll just write symbol for now. So it would be category of matrix factorizations, which are equivariant with respect to action of the Borel. And then there is this space, the stable space, stable piece of some space, and there is some potential. let me first write all of the objects on the blackboard and let people look at them. So, and for now, like G is GLN, and B is Barrel, and stuff like this. So, so that's G. All right. So, and what is the potential? Potential. So I didn't say what is sigma. Sigma is element of the symmetry group, and the potential is X, G, Y is a trace of X sigma twisted Y minus X at G twisted. Okay, so all right, so that's the potential, yeah. And the sigma acting on Y somehow. Sigma, basically this is X, it's Barrel upper triangular, this is upper triangular, this is element of the group. And I should explain what is action on the Y, the element of symmetric group. It only moves around diagonal elements. It doesn't do anything to the rest of the matrix. It's basically sigma diagonal. Okay? That's the potential. So, okay, so questions so far? So far, I didn't explain you what is matrix factorization. So, the matrix factorization, it's actually it's a triangulated category whose objects are objects of this matrix in general, more general. So, objects of the suppose you have the affine variety Z with potential F. So then the objects here would be basically two periodic complexes, D0, D1, M0, M1. All right, so and the condition is that MIs are free. And another condition is that composition of this differentials is equal function F. Okay? Yes, questions?
How many of the F by N percent by Barrel?
Yeah, I just only move diagonal guys. I don't touch the rest. Looks funny, but it works.
Fix the decomposition of B plus N.
What?
You fix decomposition B is T plus N? Or?
No, it's just upper triangular matrix. You have upper triangular matrix. You look at the diagonal part. You move stuff in diagonal. Don't touch the rest of the matrix. Okay? More questions? So if it's confusing, just think about when sigma is equal 1. For now, it's already kind of meaningful. So, okay. So then, okay, these are the objects. And, these are two periodic complexes. And there is, you can define the morphisms in a natural way. So somehow, so the morphisms are the like maps which commute with differential, and there is this like natural notion of homotopies, and you can just define the thing. And actually, this object was defined by Eisenbach in 80s, but it was actually brought in forefront of modern mathematics by I think by some email of Kontsevich, and later on was expanded by Orlov in 2000. So it's thousands. So it's kind of it's really important in mirror symmetry. So, but I will not expand on this. But I would say that the moral story of the of matrix factorizations is that, in some sense, the category of matrix factorization is a proper replacement for the category of coherence shifts on the critical loci of F. So basically, I can steal it from basically what's written in papers of Telemann. Telemann basically have a notation that this matrix factorization on ZF is a square root of a coherence shift of the category of coherence shifts on the critical loci of F. It will appear later. So this. Any questions at this point?
So what is the critical locus of?
Yes, that's a good question. That's an exercise for students, but I can do it. So. I'll do the critical loci computation for slightly smaller potential in a second, and you will see what it is. Please ask questions. So it's the last talk. If I don't get anywhere, well, it's okay. I'm the only thing between you and lunch. All right. Okay. Should have used. Okay. Now, what's the point? You know, I just defined some things, and I didn't give you any theorems yet. The point is that first of all, observation number one. I don't know, proposition. It's not a hard theorem. That if you take a union of these guys, MF sigma, and by the way, I didn't tell you what is stable means in this case. It would appear later, but essentially it means that you have a cyclic vector such that if you take this cyclic vector and apply, you know, x and y to this cyclic vector, you get everything. It's an open loss inside of here. All right. You can also work with unstable piece. It's also interesting. That's related to affine stuff, affine braid group. Anyway, so the statement is that actually this thing is a monoidal category. All right. So basically there is a natural convolution here. Well, the reason for that, you know, if you look at this potential, it has like two pieces, these two pieces. And it's like, you know, the usual story of Steinberg. So basically, maybe I'll like define this convolution later on, but it's not hard. All right. So now, more interesting statement is that there is slightly smaller potential, which I'll how should I do it now? Okay, so let me write like interesting theorem. The interesting theorem that it has a monoidal structure, but actually there is a homomorphism from the braid group on n strands inside of this category. So I'll just, from now on, I'll just abbreviate things. I'll write MF subscript dot, which is union of all of this. So that's MF subscript dot. Okay. So that's our paper from this year. It's left, and let me also say one more thing. So now this potential is big, and it's hard to take its derivative. I will write you smaller potential, which is hard to take derivative of. The potential is oh my god, so I'm talking too fast. So is this? So it's a reduced potential, which is again, it's a potential. My apologies. So basically, here it should be BB over H. So my apologies. So the correct statement should be Y1 and Y2. That's the correct thing. So that means. So basically, it's two matrices, Y1 and Y2, and there is matrix between them, but they have the same guys on diagonal. So that's the correct thing. And it's actually related to what appears in paper of Roma. He's reading email right now. There's a paper of Roma and Vilonin. They have the same kind of thing. So I think it's not the case. Anyway, so I will write something smaller potential. So it will depend only on x and y. Now this guy is in barrel. This one is in group. This is in barrel. And this potential is much shorter. So it's a trace of sigma this times minus, sorry, x times add g y. Okay? So, and the cool thing about this potential is that actually, for example, when sigma is equal 1, it's completely it's symmetric with respect to x and y. So because if you switch x and y, you have to replace sigma by sigma inverse and g by g inverse. But it is symmetric. So, and the point is that somehow this, if you define this category, we call it reduce sigma this to be MF. You can also define this table piece. So that's actually this one is a big space. So the smaller space W sigma bar, and this space here is the space, the big G B. So actually, it turns out that these two categories are the same. So they are isomorphic. So that's just another model for this. And it's so-called Knorr periodicity. Maybe I'll say something. But it's kind of a smaller model. And these two categories, they have two advantages. They have their own good things. In this story, it's easy to see how you would construct convolution on this space. But it's not obvious that you can switch x and y here. But in this category, it's kind of harder to see that you have a convolution, but it's easy to see that you can switch in x and y. Okay. So, any questions? So, all right. What that? So, no, it's some. Yes, essentially that's what's going on. So more precisely, I specialize y1 to be equal to the conjugate upper triangular part conjugation of y2. And you could see it, So basically, this Knorr periodicity fixes you this crystallization. So I'll say what is Knorr periodicity in a second, but I just want to get to some kind of interesting statement, so that something that people could possibly recognize. All right. Any questions? So now I'll go back to matrix factorization and say a couple of things. I know that, unfortunately, matrix factorizations are not like a mainstream mathematics yet. So, and I would like to mention a few features of the matrix.
What is this functor P?
What?
Do you know what this functor P was?
This functor? Well, morally, it's some kind of, okay, I can say what it is. So basically, I can explain how it's related to what people in this room know. So for that, let's just compute critical lossy of this potential. All right, that's a calculus exercise. So we all teach calculus. So, do I want to make my life easier? Okay, I want to make life easier. So, for example, let's compute the derivative of this reduced potential with respect to g. With respect to g, if you take a derivative, what you'll get? It will only this guy would appear. And actually, if you do this exercise, let's do it at the g equal 1. You would see relation that it's xy. So that's why this object is related to the Hilbert scheme. And you'll see more precise relation. All right, but let's do another derivative. Let's take derivative with respect to x. So, and let's set sigma to be equal 1. And let's take derivative of this potential with respect to x. Well, and you'll get equation that it's y minus add gy. Okay? So, and if I take, now this is the equation on upper triangular matrix and group. So if you take this, let's call this one equation E. So if you take the scheme, the group times B, mod this equation, and so this is the defining equation, and take it mod B. Well, that actually is the big Steinberg quotient GLN. So that's the same thing. So and basically, this braid group construction, braid group action is related to the papers of Roma, who is reading email, and Roma and Risch, but by some kind of possibly some equivariant version of causal duality, but it's not written. Yeah. Did I answer your question? Actually, there is also a construction of Tina and Tina Kanstrup and Arkhipov, which they also construct some action, and it's related to this. Yeah, I can. Okay, so.
What's the equation?
This is the equation. The equation is that you take matrix Y, upper triangular, conjugate it by any matrix G, and it will turn into Y, so come back to Y. And that's Yes.
I thought, sorry, but I thought that X was also number triangle line.
Yes, sorry. Yes, I said it wrong. So I apologize. The condition is that this belongs to the barrel. So yeah, that's the condition. Yes, that's the equation.
The other Borel. The other Borel.
So sorry. So like this guy is barrel. So that's the equation. If you take derivative by this, that means that lower triangular part of this equation is 0. Yes. So sorry. Thank you. It's really good to have such an intelligent audience. So and yeah.
So just to connect to some other talks in this conference.
Yeah.
The diagonal part of this guy should be 0.
Yes. Yeah.
So that has something to do with this stabilization.
It does probably has to do something with stabilization. That's what Andrew was telling me for years, and I was stupid enough not to expand on it. Yeah. All right. More questions? All right. So a few more things about metric factorizations. So the general property of the metric factorizations that you can take tensor products of them. So suppose you have a x with potential f, and you have a metric factorization with potential, and you have another metric factorization. Let's say, well, first of all, I will introduce notation. When I write bar, I just take the same metric factorization and say take inverse of every odd differential. So then, you know, now your equation, the square of differential is not f but minus f, but it's essentially, that's like a Serre duality in this category. This category is Calabi-Yau with respect to this thing. So, and all right, so now another property of this thing that if you take two guys with different potentials, and this one, let's say MF X G, right? If I take tensor product of them, what happens? Anybody know? Answer. All right, so the question was, well, I take a metric factorization with potential with the same space, F and G. I take the tensor product. It's again two periodic complex. You know, it's like bi-complex, which we can take total differential of this complex. It still would be a metric factorization. What would be the potential? But yes, that would be F plus G. So, all right. That's an important thing. So in particular, it gives us cheap way to go from matrix factorizations to two periodic complexes, honest complexes. Because if I take, for example, A and A bar, take the tensor product, then potential goes away. So that I'll write it here. Okay, so statement here that AB belongs to the category of the metric factorizations of F plus G. Okay? All right, and we will use it in a second. I'm explaining you construction of this object E from the beginning of my talk. So when do I stop actually?
So it's in 20 minutes.
Okay, that's fine. So all right, so in particular, I can do following things. Suppose I gave you this homomorphism for every braid. I construct a metric factorization, and there is one really good braid. So what is the best braid? The most canonical braid? Identity braid, yeah. So now we can take, you know, phi. This was this homomorphism from the braid group into the metric factorizations. Well, we can do what? We can take this metric factorization and smash it with the guy which come from identity and take opposite of it. All right. So so now this guy belongs to this category of the metric factorizations on this space. Well, let's look at the reduced space, this table, with zero potential, right? So, and sorry, I lied to you. You all believe me, so that's not true. It's not zero. It's not zero. It wouldn't be zero because I didn't. So it wouldn't be zero. It would be some potential. So let's explain why it's not zero. So there is some potential Q. So it would have been zero if B would have been pure braid. So in general, I didn't tell you the whole detail. I had this annoying thing that each of the for each element of the braid, you can define element of symmetry group, which is like how it permutes. And actually, each braid would appear exactly in this special category, which is labeled by this element of symmetry group. And it's kind of similar to this Yification construction of Eugene and Matt Hogenkamp. So B dot is this notation of symmetry group, right? So that's why potentials are different. You know, basically, if I do this, I don't get zero potential unless sigma is 1. But nevertheless, it's easy to check that this potential is actually, which you will get, actually it would be, would only depend on diagonal eigenvalues, diagonal values of elements that will be quadratic on this eigenvalues, and you can apply some Knorr periodicity, and you will get this object E. So, but so let me. Sorry, I think everybody is lost now, but no, okay. All right, good, good. It's not my intention to make everybody lost. So what is Knorr periodicity? It appeared a few minutes ago in my talk. Now I'll say it more concretely. So, so basically, Knorr periodicity well, it's a following statement. So whenever we have a category of method factorization on some space Z times C2 with coordinates xy, and say potential is of the form some potential, some function of Z plus xy. So then Knorr periodicity tells you that it's the same category as if you would erase this guy here. So it will be this WZ, which is consistent with my motto that basically this matrix factorization, they only know about critical loci of this potential, and critical loci here, if you take derivative, it tells you that x and y is equal to 0. Right? So, so in this guy, in particular, this potential actually would be this. So it would be sum of xi, yi, sigma y. And these are, well, I should put it like this. This is a diagonal value of x and y. And we can use this critical, we can use this Knorr periodicity. So, and I will denote this by Kn. So, and this object, which I was telling you before, so this E at the beginning, if you take a closure of the braid, then this object is you take this phi B tensor, phi B tensor. So you apply this Knorr periodicity, kill the potential. And by the way, killing the potential means that, sorry, that's the difference is like, it's xi, y, yi minus this. That's the potential. So that's, and basically that imposes a condition that y's are equal. So it basically fixes us, how to say it, if we write this thing as xi, yi, minus yi, sigma I, sigma I. So that kind of, so a priori that was a metric factorization of a ring with n y's and n x's. So but if I apply Knorr periodicity, this kind of form of potential kills us most of the variable. And after applying Knorr periodicity and taking B invariant, we end up in the derived category periodic of C star cross C star of this ring, which I wrote you at the beginning. Okay, that's the construction. Any questions? So now, and I'll denote this. So let's call it. This is actually a slightly small object. Let's denote the trace 0 of beta. So to get homotopy invariant, the isotopy invariant, we also need to introduce this A degree things, because so far we only have C stars which act by scaling C star cross C star, which scale X and Y in this construction. But you want to have one more degree, which becomes degree A, that come from this from the exterior powers of the tautological bundle. So in the precise statement is, so if I define this trace curly B to be Knorr phi B again, that's equivalent. Actually, multiplying by f of 1 is equivalent by setting g equal 1 in this thing. Exterior power of a Cn equivariant B. So now this A degree comes from the fact that I multiply by the exterior powers of Cn, where you have action of Bn. So it's non-trivial thing. So now this is this object E, which I define you LB. So in the theorem that this is isotopy invariant. So this is isotopy invariant of LB. And that's a little bit of work to show that actually it's invariant with respect to this convolution. So basically this convolution which reaches X and Y preserve this object. So that's, oh yeah, involution, sorry, involution, yes. So that's, yeah. Okay, so that was one thing. So now I need to at least address what I promised to Eugene, how Hilbert schemes appear. All right? Any questions about it?
In the second statement, you just check for the generators and then say.
Yeah, we check the generators, and you have to check that convolution. That is kind of actually F is there is a more general statement that if you have F phi, there is some kind of slightly sign twisted version of it. So if you take two guys, convolve them, then it basically switches them. So basically, it's the same as F T beta exterior. So basically, this convolution is basically is a convolution. It respects the convolution product, and actually, that's why. Okay. So and then you have to check it on generators, and it's simple computation on generators. All right. Any questions? So now, where are the Hilbert schemes? That's where I would like some comments from the audience, because there would be some symbols will appear which are familiar. Some people here. All right, so I define you this category MF dot. So, but there is another stuff which and there is some kind of extension of it which we didn't post it yet. So, actually, this category, this MF under dot, there are functors, adjoint functors. There is a character functor. So we call it categorical Chern character. It kind of has some meaning. And the category of the periodic shifts on Hilb and C2. So in this direction is HC. And we shamelessly stole notation from the paper of Bezrukavnikov, Finkelberg, and Vita. So, and I think that's. You stole it from Ginsburg. Okay, so that's good. So it's kind of sequence of stealing. So, and I suspect that's kind of a B model version of this stuff. So because we work with coherent shifts, but what are the properties? So the properties of this thing that, well, they are joint, of course. HC and CH are joint. So the other property is that it's a trace functor. CH is a trace. CH of alpha beta is obviously it's a CH of beta alpha. The third property is that well, this direction is actually monoidal. HC is monoidal. Monoidal. And it's very easy to see what happens with O. So basically, HC of O, which is the structure sheaf, is identity. It's basically phi of 1. So, well, you could ask what can we say something here. For example, another property is that if you take this character sheaf and apply it to the identity braid, you'll get Procesi bundle. So, and well, and of course, the last property is that the image, all of the guys that come here, they're central. CH, HC of anything is a center, is central in MFC. So, you know, that's kind of tells you somehow that this guy is kind of morally related to this Greenfield center of this category. And actually, there is a more precise statement. There's actually two categories where this guy, this object, is actually this category is actually is a category of endomorphism of object of two category, and this two category has identity, and it's tautologically true that endomorphism of identity in two categories is literally the Hilbert scheme of points on C2 coherence. So it's anyway. So that's and another property, the last one, that you can get our like old this E, if you want to compute the total homologies of this object, which I was telling you. So what you do, you just apply, you take object here, apply this character guy, so it's equal, basically, it's equal home of the, you take a character guy, so character applied to this, so L was the closure of B, beta, so phi beta, and well, so and you apply it to the 1, so O, and twisted by this exterior power. So it's terrible. I apologize. So times exterior power of this tautological bundle. Okay, so that's my old homologies. All right. How much I have? How much time I have?
7 minutes.
Okay. Well, I guess I have to say something new. So, why Soergel bimodules? So far, nothing remotely related to Soergel bimodules appeared. So, but any questions about this? Yes.
Is there a version where you use MR cards or?
What that?
Is there a version where you know, use some sort of scaling action on the left-hand side to reintroduce the Z grading in this relationship?
C grading. Is it? Oh, Z grading. Yeah, I mean, you know, actually, I was lying you all the way through because in this matrix factorization, I have to also tell you how the C star acts. And actually, C star, one of the C stars, it actually scales differential by weight 1. If that was your question. And that's why, you know, basically what would appear later, it's important for this connection with Soergel bimodule. Somehow, even though I talk about two periodic things, I can actually restore my restore everything back to normal complexes. So because of this grading. Did I answer your question? Yeah. So, and that's important for what's coming. All right. All right. So now Soergel bimodules. So 5 minutes is enough to explain it. Actually, this connection with Soergel bimodules is kind of outlined in this paper which posted a year ago. We didn't expand on it, so now I'll just expand on it more. All right. So relations with Soergel with SB. All right. So I will introduce this new category, MF sigma prime, which is closely related to all of these categories. It's equivalent to this to a version of this category. So that's the ambient space, and the potential is the same as before. Okay, but it's different in the sense that I don't constrain the. So I don't constrain. So let's do it like this. So this guy is let's just write this potential. It's if this is x, g1, gi, yi. So the potential is it's add g1 sigma acting y1 minus add g2 tau acting y2. Okay, so that's the potential. All right. So now I will construct your functor to bimodules. So that's the functor from this category. So and the point is that this category is equivalent to the other kind of the version of the category which I did not discuss, which is so that basically if you take union by sigma and tau, let me just so that's the statement tau here. So the point here that if you take union of these categories, so even though the sigma and taus appear, they kind of, you can get rid of them. So the point is that this category is equivalent to the category of matrix factorizations on something that we studied before. So it was a so it's here it would be nilpotent and it would be group and B, and the potential is x, g. Y would be even simpler. It's a trace of x and g. Y. So, sorry, I don't have time to explain it why that's the case. The point is, but in this realization, it's easy to construct a functor to the bimodules. So the bimodule functor is you take object here, see here, and what do you want to do? You want to get rid of potential. There's one stupid way to get rid of potential. Set x to be equal 0. You set x to be equal 0, and you take b square invariance. So basically what happens here, you take this and that definition of the functor. So the bmod, like you take the complex, you set x equals 0, and you take invariant with respect to action of b2 and g. So g acts by conjugation by g1. And it's not hard to see that this way you'll get bimodules, because you still remember the the bimodules is when you have an action of the one polynomial ring and another one on left hand side and right hand side, and we have one polynomial ring comes from the diagonals of y1 and another one from y2. So and that's bimodule tautologically. So the one thing you need to show somehow, Soergel bimodules, they're special ones, right? So and they correspond, Soergel bimodules, they correspond to this Kazhdan-Lustig basis in the Hecke algebra, and we can just produce explicitly these Kazhdan-Lustig elements in this category of matrix factorizations. So I don't have time to explain it, but they related to this kind of fat graphs. Instead of working with the braids, you can work with this like MOI calculus, and that kind of allows us to construct the some kind of statement. Let me just write a statement and I'll finish. So it's not that we construct kind of isomorphism between our category and category Soergel bimodules. We prove much weaker statement. So let me write a statement and I'll finish. That would be enough. Statement is, as talk goes, I feel stupid and stupider. That's why I have to look at my notes, closer to the end. So here, the statement is that. Okay, I apologize. So.
No, but that's true for any
So. I don't have time to explain it, but there is some kind of a subcategory inside of this category MF. Let's call it MF flat, which is generated by, so basically like in usual, you can study instead of braid groups so-called flat graphs, and there are some kind of objects you can attach some metric factorization to any flat graph. I don't have time to explain it. And the statement is that this trace, which I explained, you can still apply it to this object. And the trace of the statement is equal to the Hochschild homologies of this beam applied to C. That's the main statement. That's enough to show that, and then corollary of this statement is that this global sections of this object Ex, E L L beta, and we have to kill one of the set of variables R Y, that it is equal to, you take how it goes. You have to take. That's the definition. Sorry, I'm just writing it I'm butchering this definition of the Havanov and Rozansky, but that's their definition. So their definition is that. So I've said something terrible. So you have a beta, and here you need to put this Ruchia complex attached to the beta. But Ruchia complex is made of these flat graph guys, and since our functor is actually it's a functor, it's functorial. You don't have to check any consistencies. It's enough to prove this, and that implies everything. So I'm sorry, I just rushed it then. So, but I can explain people privately how it goes.
Questions?
So do I understand correctly that this category that you relate to Soergel's bimodule, it's also right to the Hirschman on the Steinberg?
Yes.
Then
That's an
that is
unstable piece of Steinberg, as we discussed. This kind of, yeah. So yeah.
but that is has a somewhat clear relation to Soergel's bimodule.
But yes.
This has a clear relation to Soergel's bimodule. Maybe I find it.
Yeah, so fine, but it's kind of important that we do stable piece. So because, in this construction here, I didn't explain it. We kind of use that there's this Markov move, which reduces number of strands. And we don't know how to do it without stability. So that was your question. So it's important. I don't know how to prove, your theorem this way. Because if you remove stability, we don't have this trick. So, I kind of really use the fact that this E guy is a topological invariant. I use this fact that we have a Markov move. Without it,
It should be related to this.
it probably is.
Okay.
Well, as you said at some point, everything related to everything. So, yeah.
So, from the physical motivation, does this space on which you take factorization is related to some Stokes data? Kind of flat connection?
Maybe. So, there's some physics interpretation of this gauge sigma model. So you can watch my lecture in Edinburgh. I tried to explain it there. And there is also a paper on archive that really explains it. Yeah.
Other questions? So what's the idea of the proof?
Well, idea of the proof, we have to read Jake's paper, Jake's Rasmussen paper. So, he has this paper calculus, how he can, well, on this side, on the Soergel bimodal side, there's this way of working with these flat graphs and kind of, you can compute, there's a calculus for computing homes between flat graphs, and it uses this Markov moves. And the same, and we prove that the same calculus works on this metric factorization side. So basically that's, the idea of the proof, there's this relation. So let me write one relation, maybe that would answer things. So there's this relation, so, terrible. How it goes, like this, right? This plus x, y, this is equal, right. So the knot theory people will recognize this thing. That's relation on the fat, not in braids, it's relation on these fat graphs, so it's relation on this. Right, so this. And then there is this kind of relations how you would relate, this thing is equal this times C, some kind of factor here. And there is this kind of set of relations. And it's true for these fat graphs, and we check that the same is true on this flat piece of this metric factorizations. And then it's tautological, then they match. Because there is some kind of algorithm how to reduce computations on this side basically to bunch of unknowns. So, and the same true in this metric factorization set. Sorry, you don't look satisfied. Yeah.
Other questions? Okay, let's thank the speaker again. And that concludes our today's schedule, so we will reconvene tomorrow at 9:30.